Hello everyone, I'm Shinichi Awamoto. In this presentation, I'm going to talk about a novel storage software stack for accelerators we built. As Moore's law is slowing down, accelerators are expected to grow in the market for high throughput, low latency, and energy efficiency. The prosperity of GPUs is needless to say. There are a wide variety of domain-specific accelerators. The one we are interested in is SoC-based accelerators. As opposed to the offloading-based computation model of GPUs, they can execute the entire application code by themselves. This means that they do not require constant communication over PCIe with the host during data processing. However, I/O access still requires a mediation by the host OS running on CPUs. This CPU-device communication overhead is high enough to impact response time. When we see the breakdown of the end-to-end execution time of a bioinformatics application, most of the time is spent to load data, while the accelerator can process data efficiently, benefiting from specialized cores. From this result, we conclude that the storage I/O inefficiencies significantly impact on the end-to-end latency and throughput of such accelerator applications. So specifically, what causes this performance problem? The red line of this figure illustrates how system calls are handled on some accelerators. Multiple data copies in dispatch is required in the host user space and kernel. And this is clearly inefficient. In our experiments, invoking the fcontrol system call on the host takes 105 nanoseconds, while that on the accelerator takes 43 milliseconds. Moreover, if the system call is read or write, Linux will also access to the storage medium over PCIe, which means the data prepared by the disk is passed around inside the host system. This high system call latency and data copy overheads slow down file operations. This is obvious from this graph, the comparison of read and write throughput performance between the host and the accelerator. There are several design options to tackle this problem, but none of them are workable in this case. First, buffer cache sharing between accelerators and storage medium mitigates data copy costs. But device and file management is still mediated by CPUs. Second, since there are no kernel contexts in some accelerators, it is impossible to run heterogeneous kernels in it. Third, we also tried porting conventional system software on the accelerator. However, we found out that this approach resulted in poor performance from the evaluation of ext4 file system. This graph shows the file access latency of RAMFS and ext4. Even simple read and write operations are enough to compare the performance of them. And we deduced that porting conventional system software to accelerators is a bad idea. Therefore, we built HAYAGUI, a novel user space storage stack for SoC-based accelerators. The built-in NVMe device driver manages SSD medium, thus it does not require any help of the host system. This direct storage I/O framework consists of 3 layers for portability. Each provides raw I/O, file system providing the buffer cache, and LevelDB ported to the accelerator. Application programmers can choose the most suitable interface for their application. A key aspect of this challenge is how accelerators handle raw NVMe interface. First, since SSDs are managed by the host in most cases, we have to detach the device from Linux. We use the Linux user-space I/O framework, but this is just for granting the access right, and UIO itself does not do anything for device management. The SSD is controlled entirely from accelerator's memory space. Not only DMA buffers, but also device registers are mapped in there. These remappings are performed by vendor-specific PCI APIs. If the application requires the fastest way to handle data, the direct I/O engine would be the best option. On the other hand, most applications need a file system API, which manages multiple files with names or inodes. File system also plays an important role to improve performance, which is, for example, deferred write I/O and responding cache data. As I've already described, we could not use conventional file systems because of accelerators' performance limitations. This AccelFS is an ext2-like file system, but it's carefully designed to cover the weakness of general-purpose cores, such as slow malloc and atomic operations. We also ported LevelDB for applications that use key-value store as their storage backend. We are planning further improvements for both AccelFS and LevelDB to exploit the specialized computing power of accelerators. This will release application programmers from tricky optimizations to implement efficient system software on accelerators. To evaluate our direct I/O framework, we used NEC SX Aurora Tsubasa Vector Processing Unit. This commercial product implements vector core as a specialized computing units and high bandwidth memory modules on one chip to process a large array of data with one instruction. Its high computational capacity is currently used for image processing, risk calculation, weather prediction, and so on. Although this accelerator is often used in the HPC field, I believe that the key idea can be applied to any other SoC-based accelerators. First, we tested performance of HAYAGUI with simple file operations. The baselines are measured with read, write, and fdata sync system calls. And invoking these system calls is always mediated by the host. Direct I/O uses NVMe sync command instead of the fdata sync system call and treats the whole NVMe storage as a single file. From this graph, it is obvious that the latency is reduced dramatically by HAYAGUI from 20 to 99%. Moreover, the difference in performance is little between direct I/O engine and our AccelFS. In this experiment, we measured performance of specific key value store operations with and without HAYAGUI. DB-Bench is the main tool to benchmark LevelDB's performance, which can be found in the LevelDB's repository. For many different types of workloads DB-Bench can generate, we chose 5 major ones: sequential read and random read, sequential write, random write, and sequential write with buffer sync. Whether it is sequential or random, the request latency is reduced by 33 to 81%. We also tested LevelDB with realistic workloads via YCSB. Unlike DB-Bench, YCSB generates mixed operations in each workload. We chose 4 major ones from core workloads, which is known as workload A, B, C, and D. With HAYAGUI, the throughput is improved by 12 to 89%. This result implies that our design would work in various and complex operation patterns we often face in real applications. This graph shows the evaluation result of a bioinformatics application. This application loads genome data taken by a DNA sequencer and analyzes the data efficiently with vectorized processing. We use datasets from multiple species in this experiment. And this is because data size varies among species. Although its data is huge, from 2 gigabytes to 15 gigabytes, not as key value store workloads, HAYAGUI saves this data efficiently and demonstrates that it has a potential of accelerating real applications. To conclude, we propose HAYAGUI, a novel storage stack to solve the I/O issues of accelerators. This storage stack can directly control storage medium without any support of the host system, which leads to fast data access. It consists of 3 layers to meet application's demand, and we demonstrate that it outperforms the system call redirection baselines. Although our direct storage architecture seems promising, there are further research questions. It is not clear that direct storage access is applicable or sensible in other accelerators. General-purpose cores in accelerators are not broadly like Xeon processors. We observed that atomic operations and malloc are extremely slow on the NAC accelerator, and other accelerators might have their own limitations, which would become an obstacle of designing a generic storage stack. Another interesting topic is how we can gain the benefit of accelerators to design a storage stack. Their specialized computing units would cover the weakness of wimpy general cores. Our current design dedicates an entire storage device to the accelerator, but to achieve a shared namespace across the whole system, a distributed architecture might be worth considering. That's all. Thank you for listening.